To wrap up this week's topics, we're going to look at determinants. This is another calculation that we can do on matrices, and it will link to the idea of matrix inverses because if you remember from the last slides, calculating a matrix inverse using the technique we have at hand requires Gaussian elimination. That can be tedious, and so before you leap into Gaussian elimination to find the inverse of a matrix, you might want to know if the matrix is going to have an inverse to begin with, because if it's not, you don't want to waste your time doing the Gaussian elimination. Determinants can help us with that, and determinants can help us with other things too. So what are determinants? How do we calculate them, and how do we link them back to matrices? Now, the end of the story, I'm going to spoil. It's coming up right now. The end of this story is that if a matrix has a determinant, and we haven't talked about what determinants are, but just go with it. If the determinant of a matrix is 0, then the matrix will not have an inverse. And if the determinant of a matrix is not 0, then the matrix will have an inverse. So you have a matrix, you want to know if it's going to have an inverse. You can calculate the determinant of that matrix, and if that determinant is 0, you know not to waste your time doing Gaussian elimination to find the inverse because there won't be an inverse. For the moment, just think of the determinant of a matrix as a measurement of the data inside the matrix. The determinant of a matrix comes out to be just a single number. So a 2 by 2 matrix has a determinant, which is just a number. A 3 by 3 matrix has a determinant, which is just a number. Okay, and it kind of measures the data inside the matrix, sort of like an absolute value will measure a number. And we even borrow that notation. So det parentheses A means determinant, and so does a matrix name like A with bars around it. That means you're looking for the determinant. Here's something you just have to memorize. If you have a 2 by 2 matrix, the determinant is formed like this. You just do crisscross products and subtract. So the determinant of the matrix ABCD, just multiply the forward diagonal, multiply the backwards diagonal, subtract the results. There's an example. So the determinant of that matrix is 3 times 1 minus -1 times 2. So 3 plus 2, that's 5. To do the determinant of matrices matrices that are bigger, like 3 by 3s, we're going to decompose the 3 by 3 matrix or a 3 by 3 determinant into a sequence of smaller 2 by 2 determinants. So if you know how to do 2 by 2s, you can do everything else. Oh, and yeah, since the determinant of this matrix wasn't 0, that means we could spend time finding the inverse and it would be there. So here is what the determinant of a 3 by 3 matrix looks like. So see what's happened is that the determinant of the 3 by 3 matrix is going to be calculated using 3 smaller 2 by 2 determinants. There is a pattern to this. See if you can figure it out. The first term on the right-hand side takes that entry A11 and it multiplies it by a 2 by 2 determinant. Can you see where those 4 numbers in that 2 by 2 come from? And then move over to the second term, which has the entry A12 multiplying a 2 by 2 determinant. Can you see where the 4 numbers in that 2 by 2 determinant came from? Are you finding the pattern yet? What happens is we've gone across the first row, we've stopped at each entry. At each entry, we just erase in our heads the row and column that entry sits in. The 4 numbers that are left get collected into this new 2 by 2 determinant. Also note that there is a subtraction in that middle term. That's not a typo, that belongs there. We'll see why later. But this is how we do a 3 by 3 determinant. So, example. Here's a 3 by 3 determinant. What we're going to do is crawl across the first row, and we'll take the entry -2. In our heads, we'll erase the row and column that -2 sits in. That will leave us the 1, the -4, the -6, and the 1, and we'll form that 2 by 2 determinant. Then we'll move over to the 0 in the first row. We will erase its row and column, leaving behind the 3, the -4, the 2, and the 1, and then the same thing for the 5. And remember, the minus signs will go plus, minus, plus on each of those terms. We can evaluate each of those 3 2 by 2 determinants by doing the crisscross multiplication with the subtraction. And there's a lot of numbers here. Pause this if you need to trace the numbers through. The value of this determinant turns out to be -54. So again, we have a 3 by 3 matrix, and we know that this one would have an inverse, and we would not be wasting our time trying to find it. Okay, so this method that we looked at for calculating the determinant of a 3 by 3 matrix is called expansion by minors. You take a 3 by 3 determinant, you go along the top row, and you expand your calculation by minors, by smaller determinants, those 2 by 2 things. It turns out that we can expand along any row or column in a matrix to find its determinant. In the last problem, we saw that that 0 in the top row helped us out because the minor that went with that 0 got multiplied by a 0, so it didn't really matter what it was. It speeds up the calculation. So if you always want to just expand along the top row, no questions asked, I suppose you could stop the video now and just always plan on doing that. But there is strategy to picking other rows and columns, so we're going to talk about it a little bit further. And that involves something called cofactors, and this is going to explain where that minus sign came from in that middle term of the 3 minors from before. So remember that that middle term was a minus in that big expansion of the 3 by 3 determinant. The terms went plus, minus, plus. They were alternating. And that's because each term ends up multiplied by either a plus or minus 1, and which one you pick depends on where it sits, what its entry is. Okay, so if we go to a 3 by 3 determinant or bigger, and we take an entry in that matrix, in that determinant, and we erase its row and column, the 2 by 2 determinant that's left is called the minor that goes with that entry. The entry sits in row I, column j, and so the sum of I plus j goes on an exponent of minus 1. So minus 1 to the I plus j is multiplied by the front of those terms. We'll see this laid out in just a second. But the bottom line is that the 2 by 2 minor determinant multiplied by this either plus or minus 1, depending on the position, is called the cofactor for that entry. And those minus 1s with the exponent are what turn on the plus minus signs. Okay, so here's that expansion again. That determinant of 2 by 2 that we see 3 different times in that expansion by minors, that 2 by 2 determinant coupled with the either plus or minus 1 in front are called the cofactors. And so that kind of longer, messy expansion on the right-hand side can be written out as cofactors, and that tidies it up quite a bit. Okay, and each cofactor, again, is just the 2 by 2 minor determinant with a negative 1 in front. The power on that negative 1 is the sum of the row and column. So entry A11 is in row 1, column 1. So its cofactor is negative 1 to the 1 plus 1 times the corresponding minor determinant we get when we erase the row and column. Entry A12 is in row 1, column 2. And so its cofactor is negative 1 to the 1 plus 2, and that's negative 1 cubed, which is negative 1. Aha, that's why that term is negative. And then with the 2 by 2 minor determinant attached, and then A13 is in spot row 1, column 3. Negative 1 to the 1 plus 3 is positive 1. And that's why the alternating numbers happen in that expansion by minors. Okay, so we can really expand along any row or column. So in this case, I've expanded down the second column. So I've gone through entries 1, 2, 2, 2, and 3, 2. And at each case, I would stop. I would erase the row and column of that entry and gather the 4 numbers that are left into a minor determinant. And I would multiply each term by a power of minus 1, depending on the sum of the row and column. So here's an example. We're going to calculate the determinant of this particular matrix. Let's look at the rows and columns and notice that, column 3 has 2 zeros in it. So that one is going to be the easiest thing to expand along because the terms with those entries will vanish quickly. So if we're going to go down column 3, we're going to go to entries 1, 3, 2, 3, and 3, 3. That's row 1, column 3, row 2, column 3, and row 3, column 3. We're going to take each entry, form the cofactor that goes with that entry by erasing its row and column and forming the smaller 2 by 2 determinant and putting on the power of minus 1. So minus 1 to the 1 plus 3 times the 1, 3 minor determinant times 0. And then go to the 3 in that third column. Take that 3, multiply it by its cofactor, which is that 2 by 2 minor determinant when we erase the 3's row and column, times the proper sign of negative 1, and etc. Now the first and the third terms are multiplied by 0 because those are the entries themselves, so we're not even going to write them down anymore. The minor determinant for entry 2, 3, for that number 3, the numbers that are left there for that minor are 2, negative 4, negative 2, 1. Calculate that determinant, and so the determinant of this big matrix is 18. That matrix would have an inverse. And that's it. So calculate determinants to find out if matrices have inverses, and we'll talk about other uses of determinants some other time.